This is my drone, and at any point in time, it's either on the ground or flying. Two clear states, up or down, flying or landed. But life isn't this binary at the quantum level.
The quantum level? Yup. The level at which electrons, protons, and the recently discovered quartz particle exist. These particles follow the rule of quantum mechanics, hence the name. Too complicated? You know what? Forget it. Let's just think about cats. Yes, cats.
Just like Erwin Schrödinger. His famous thought experiment was about putting a cat in a box with a radioactive element that had a 50% chance of decaying and killing the cat, or not decaying and leaving the cat alive. But let's say we haven't opened the box yet. In this case, we aren't aware whether the cat is left alive or dead, hence placing it in a superposition of dead and alive at the same time. Quantum particles have certain properties, such as but not limited to position, where they are, spin, which direction they are spinning in on their own axis, and momentum, which is nothing but a product of their mass and velocity.
Until observed for a definite property states, these particles exist in a superposition of all allowed states simultaneously, just like the cat before we opened the box. But shouldn't be able to know at least something about these particles? That's exactly where Erwin Schrödinger comes back to the rescue. Using his famous Schrödinger's equation, we're able to solve for the wave function, denoted by Greek letter psi, that represents the probability that the quantum particle is in a particular state. What is the rest of this ancient script? For starters, I and h bar are just numbers. The value of I is the square root of -1, while h bar is a Planck's constant. Next, this is the d by dt part, which measures how fast something changes with respect to time. One of the most important parts of the equation is the h hat. The Hamiltonian operator, just like other operators, does something or operates on the quantum state. The Hamiltonian operator in particular represents the total energy of the system. So in essence, the Schrödinger's equation is a wave function changing with respect to time in a specific way, depending on the total energy of the quantum system. To actually solve this equation, we use the de Broglie relation, which states that a particle's wavelength equals the Planck's constant divided by its momentum. With that, we construct many plane waves and then apply a Fourier transform to merge these plane waves into a single superposition waveform.